5.2 to look at this as well. If I'm catching my timeline correctly, I think I've got a few more minutes to get to 10. Find the Riemann sum for this function on this interval using 5 equal subintervals. Note, this interval is 10 units wide, 5 equal subintervals. Each subinterval would be 2 units wide. And if you sample the right endpoints, the right endpoints of your intervals, if you actually look at this picture, just taking the intervals for what they are, the right endpoints would be -4, -2, 0, 2, and 4. So we're going to evaluate f of -4, f of -2, f of 0, f of 2, and f of 4, those to be the heights of our rectangles. The width of each rectangle is 2 because our whole domain was 10 units wide. We have 5 equal subintervals. Each subinterval is 2 units wide, which you can see in this picture. Now, is this a correct picture? It doesn't look like it because looking at the height of this first rectangle, that is determined by the function value on the left endpoint of our first subinterval. Going down below, oh, that's not between our function and the x-axis. That can't even possibly be. This is also not between the function and the x-axis. Ooh, this is between the function and the x-axis. And note, this is using right endpoints. So among the two function values on the first subinterval, here we're using the right of the two to determine how tall our rectangle is. And so, yes, indeed, this would be our appropriate sum with respect to net area rectangles with respect to the x-axis, I would think. A Riemann sum is always between the function's graph and the horizontal axis. So I would think that x-axis is the correct answer there. Let's see. Okay, graph of f of x is given. Oh, estimate, right? I mean, so here, just we're going to use our best judgment here. 5 subintervals. So here's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's the whole picture essentially of what this graph is the graph is existing between 0 and 10. Using 5 subintervals, we'd go from 0 to 2 for the first, 2 to 4 for the next, 4 to 6, 6 to 8, 8 to 10. Using right endpoints, we'd evaluate f of 2 or -1 to determine the height of our first rectangle. So the first rectangle has a height of -1. It has a width of 2 because all the rectangles have a width of 2 on a domain of 10 units wide that's divided into 5 subintervals. Let's see, the next rectangle using right endpoints would have a height of f of 4, which is 1. So the first rectangle would be beneath the horizontal axis, -2 units of area. And the next rectangle would be above the horizontal 2 units of area. In fact, using right endpoints between 0 and 4, those two amounts of area would cancel each other out. And we'd be essentially starting from scratch when we would compute f of 6, which would be 3. 3 times 2 is 6. That would be the area of the rectangle that would exist between x equals 4 and x equals 6 on our third subinterval, whose height is dictated by the right endpoints. If you want to use the midpoints, don't evaluate the left or the right point on every subinterval, evaluate the point in the middle. So for the first subinterval between 0 and 2, evaluate at f of 1 or evaluate to be 2 for the height using midpoints. So fortunately in this picture, the midpoints compute to be whole numbers that we're evaluating at. So it'll be going through I believe, based on the picture, lattice points on our XY plane. So we don't have to do any real guessing in terms of what the function value is. I think we're supposed to assume that we go through the lattice points. And I bet if we hit this info button, this is for visually impaired students, you can see it very precisely. So if you're ever concerned whether or not you're reading the graph correctly, don't hesitate to hit the info button because the info button will tell you plainly exactly what you are supposed to be looking at. Because in fact, the info button is there for somebody who can't see what's going on. So yeah, whether we can actually see or not, it still helps to have it just articulated really nicely. Right, here's a similar situation to what we saw in a previous example in the last section, which is we don't have a graph of the function, we don't have an explicit expression for the function. Hey, but we've got the actual values, which is very beneficial because we can use those actual values to determine the heights of our rectangles. So the heights of our rectangles are going to come from these f of x values, depending upon the situation. Now, if we're going between 3 and 9 using an R3 computation, that's a right sum with 3 subintervals. So let's see, we go from 3 to 6. No, we go from, let's see, 3 to 5, 5 to 7, and 7 to 9. So between 3 and 5, the right endpoint is minus 0.5. Between 5 and 7, the right endpoint evaluates to be 0.9. Between 7 and 9, the right endpoint evaluates to be 1.8. So when we're doing our right sum, our heights are going to be minus 0.5, 0.9, and 1.8. If we do our left sum, we're going to have left endpoints of 3, 5, and 7, which means our rectangle heights are going to be minus 3.5, minus 0.5, and 0.9. And remember, each of those heights has to be multiplied by 2 because the width of each subinterval in this case, total domain width 6, broken into 3 subintervals, each rectangle would be of width 2. Midpoints, well, hey, on the first subinterval between 3 and 5, just grab f of 4 to be your function height. So that's the name of the game there. Right. What about this limit here? The delta x is your rectangle width. We're going between 0 and 3, so 3 has got to be up here. And then what's in here? Just the expression for our function. Looking at what is evaluating here, it looks like we have e to the x over 7 plus x, because we're essentially plugging in x sub I for our individual values. X sub I is just a shorthand notation for a plus I delta x. So x sub I shorthand for a plus I delta x. A plus I delta x is a more explicit form, probably more useful, frankly, but the x sub I works just as fine. Expresses integral as a limit of Riemann sums. Okay, fine. So let's see. The width of each subinterval, we've got 2 units total. Each subinterval is 2 over n wide. What is the ith endpoint? If we're using a right sum, each one is of the form 1 plus I times delta x. The delta x is the width above. So you'd have 1 plus I times 2 over n. So I believe this would be, if I write this out, 1 plus, based on the numbers that I've been given, 2I over n. Again, the width here is 2 over n. The total width is 2 divided by the number of sub-intervals. F of xi, you literally just take this x and plug it in for x. Like, that's not that hard. It's going to be a clunky expression, but whatever. And then here, you would have f of xi times delta x. So, okay, I won't write, but I'll just write it like this. Can I write like delta? Oh, shit, that does work. Okay, great. So we can go delta x and then times, this should be f of x sub I, which realistically, right, we know what x sub I is. We did it before, 1 plus 2I over n. Now, yes, WebAssign will not take this to be your answer because delta x was 2 over n, and f of 1 plus 2I over n is square root of 5 plus 1 plus 2I over n squared. But yeah, it's going to get clunky to write that all out, but this is the basic idea. This is always the basic idea whenever we're computing the area under a functions graph. Oh gosh, look at that. That's no width, right? So we aren't even experts at evaluating definite integrals yet, but if you have no width, I guarantee you have no area. So this should evaluate to be 0. Here we can actually use our summation rules to work this out, noticing that 5, the area under the function 5 can be computed directly because that would be a rectangle. So when you break this all down, do we get a summa symbol? I don't even know if we have a summa symbol, but okay, whether we have a summa symbol or not, this would break down to the integral from 0 to 1 of 5 dx minus 3 times the integral from 0 to 1 of x squared dx. Now, the integral from 0 to 1 of x squared is 1/3, but the integral of 5, you can literally just draw yourself a horizontal line 5 units up and then compute the area of the box that is beneath that function's graph. This is using a technical tool that we discussed today about the sum being equal, or the whole being equal to the sum of its parts. So this is the integral from a to b plus integral from b to c equals integral from a to c fact. It happens to be expressed in a lengthy form, but if you take this area from -2 to -1 and subtract it away, now the area from -2 to 2 is only going from -1 to 2. So you go from -1 to 2 and then from 2 to 3. I get -1 to 3 whenever I take away the area that we're not considering and consider the areas that we are. So yeah, that's this is a really nice example, by the way. That'd be a hell of a test question, frankly. Yeah, express this limit as a definite integral. Note the 1 over n is being factored out. That's our width of our rectangle. And the rest of the business is the evaluation. Now, we're going from 0 to 1, so within this parenthesis of I over n should probably be 0 plus I over n. That'd be the easiest way to see it. But the function itself is just 2 over 1 plus x to the 6th. So I see 2 divided by 1 plus x raised to the 6th. That's what I see in there. The 1 over n is the width of each rectangle. That's been factored out of our sum, which is perfectly fine. That's just using distributive property. Right, greater function, greater area. We talked about that in class today. Well, actually, this one might require a property that we have not yet discussed, as it turns out, because these bounds from 7 to 2 are backwards. As it turns out, when the bounds from 7 to 2, when the bounds get flipped top to bottom, the integral evaluates negative of what it would otherwise. So if you play that out, we're essentially subtracting the integral from 2 to 7. And if you subtract the integral from 2 to 7, you end up with the integral from 0 to 2. So that works out. And yeah, this, what is greater function value should have nothing to do with slope. I can imagine a very sloped thing that is well below something that is completely horizontal. And so, yeah, this is creating a connection that just doesn't exist. But yeah, okay. Well, anyways, I went a little bit over time that I was expecting. So maybe I was closer to 20 minutes, but I did get to go through pretty much everything. Oh, shoot. I see here, deduct 25% for each submission used beyond one. I really don't love that. Yeah, I'll have to think of some way that we can manufacture some. Oh, that's just, oh, that's so harsh. Anyways, I want to reflect on that right now. We'll talk about that another time. Hopefully this video can be helpful. And yeah, that's that.